In this video, we are going to discuss two demonstrative examples just to have an imagination of how FM and PM signals they look like. So what we have here is, it is given that we have a signal m of t that's periodic. It goes from -1 to 1 with a period 2 to the power 2 multiplied by 10 to the power -4. And we want to use this signal to modulate a carrier with FM one time and PM one time and see how they look like. It is given also that Kf in this example equals 2 pi 10 to the power 5 radian per second volt, and Kp is given as 10 pi radian per volt. So Kf and Kp are given. Also the carrier frequency Fc is given as 100 megahertz. 100 megahertz. Of course we know, let's start with FM. Of course we know that for FM, the carrier frequency F at any time equals Fc plus Kf m of t over 2 pi. Why do I divide over 2 pi? Because in the previous equations, in the previous video, we studied the carrier as omega. So it was omega equals omega c plus Kf m of t. Now if we talk about F, you have to divide by 2 pi. So it will be F at any time instant equals F at any time instant equals Fc plus Kf over 2 pi. You have to divide by 2 pi. So here we have m of t. First we have the carrier frequency, it's 100 mega plus Kf over 2 pi. Kf over 2 pi is 10 to the power 5 multiplied by m of t. And m of t, it changes gradually from -1 to 1 and then from 1 to -1 and so on, right? So at the peak, it will, when m of t reaches 1, okay, this will be 100 megahertz plus 10 to the power 5 is 0.1 mega multiplied by m of t. At the peak, when m of t reaches 1, this will be 100 mega plus 0.1 mega, so this will give you maximum frequency of 100.1 megahertz. And when m of t at the minimum value, when m of t reaches its minimum value, -1, then this will be 100 minus 0.1, so it will give you a minimum frequency of 99.9 megahertz. So this is the maximum frequency and this is the minimum frequency. The maximum frequency happens when m of t reaches the peak, its peak, and the minimum frequency happens when m of t reaches the minimum. In order to plot the wave, in order to sketch the waveform, we care more about the frequency, because if the frequency of is high, we can just plot or sketch some periods that are very small. If the frequency is low, then we can sketch some wide signal with wide periods. So sketching, in order to sketch, we need to have an idea about whether the frequency is high or low. If the frequency is high, we can plot like a signal with high frequency like this. If the frequency is low, we can plot a signal with low frequency. Here in this example, the frequency changes gradually from minimum 99.9 up to the maximum, which is 100.1. So the frequency here reaches 100.1 mega. The frequency here is 99.9 mega, and in between it changes gradually. Of course, sketching such a signal for you, it will be maybe difficult a little bit. That's why we said that these are demonstrative examples. These examples are just to give you an idea of how they look like. But you are not required to plot or sketch such an example with your hand. It's very difficult, especially this example, because the frequency is changing gradually. But what you will notice here is that at the peak of m, when m reaches its maximum, the frequency here in this part the frequency here in this part will be at the maximum frequency, at the highest, and you will notice that here the periods are very small. The periods of the period of the signal is very small. While when m of t reaches the minimum value, you will notice that in this area here the frequency reaches its minimum value, and the period of the signal that sketches, I hope you can see it clearly in the video, but the period here will be large compared to this one. So here the frequency is high because m of t was high, and here the frequency is low because m of t is at its minimum, and in between the frequency changes gradually from being high to low, and then from low to high again. So this is how we sketch the FM signal. On the other hand, for the PM signal, we need n dot, because for the PM signal, if we go back to the equations, so this is for the FM, this is FM. For the PM signal, we have the frequency. If we go back to the equations of the PM, you will find that the frequency is proportional to m dot. And then instead of Kf, we have here Kp. So this will be Fc 100 megahertz plus Kp over 2 pi. Kp is given as 10 pi over 2 pi, this is 5, multiplied by m dot of t. What is m dot? In order to obtain this expression or the values of this expression, we need m dot. What is m dot? M dot is the differentiation of m. So m now is increasing in this part from -1 to 1, right? So it has a slope of delta y over delta x, where delta y is 2, right? It goes from -1 to 1, so delta y is 2. Delta x is half of a period, but the period is given as 2 10 to the power negative 4. So half of a period will be 10 to the power negative 4. So the slope here, m dot here, in this area or in this region, it will be delta y over delta x, so it will be 20,000. 10 divided by 10 to the power negative 4 is 20,000. This is because m of t was increasing, so the slope is positive. In the other region, where m of t is decreasing from 1 to -1, then the slope will be, in this region, the slope will be negative 20,000. That's why if we plot m dot of t, you will find that it's either 20,000 here or negative 20,000. And then it goes back to 20,000, negative 20,000. So m dot takes only two values. In contrast to m was gradually changing between -1 and 1, gradually changing. But m dot takes only two values, 20,000 or negative 20,000. So when you calculate the frequency, you will get only two values for the frequency. Either 100 mega plus 5 multiplied by 20,000, which is 100,000, or 100 mega minus 100,000. So this will give you 100.1 megahertz, and this will give you 99.9 megahertz. So when m dot is 20,000, this will give you high frequency constant in this region, which is 100.1 megahertz. And when m dot is negative 20,000, this will give you low frequency, constant low frequency of 99.9 megahertz. What's the difference between PM and FM in this example? In FM, the frequency was changing gradually between 100.1 to 99.9, and then from 99.9 to 100.1 again. It changed gradually. But here, the frequency doesn't change gradually. It's fixed here for 100.1, and then suddenly it changed to 99.9, suddenly it changed to 100.1. So the frequency here doesn't change gradually. Actually, it takes only two values, either 100.1 or 99.9. While here, it was changing gradually, taking all the values between 100.1 and 99.9. All the values will appear here. So this is the difference between PM and FM in this example. Let's look at another example. The other example, M of t is given as a square wave. M of t is given as a square wave. And then we are required also to sketch the wave for FM and PM. Okay, and Kp here is given, in this example, Kp is given as pi over 2 radian per volt. Kf is given as 2 pi 10 to the power 5, and then again Fc is given as 100 megahertz. Doing the FM signal, there is no problem with the FM signal. The FM signal will be similar to the PM signal in the previous example, because in the FM signal, F of t equals Fc plus Kf over 2 pi M of t, and M of t here takes only two values, either 1 or -1. So this will be 10 to the power 5 multiplied by plus or minus 1, and Fc is 100 mega. So this will give you either two values only, either 100.1 megahertz fixed or 99.9 megahertz fixed. And there is no gradual change because M of t doesn't change gradually. M of t is either 1 or -1. So the frequency will be either 100.1 mega or 99.9 mega fixed. So this is similar to the PM, similar to PM in the previous example. No problem with this. I don't see any problem with this. The problem or the trick or the new thing that we are going to learn will be with the PM. When we consider the PM. When we consider the PM, we need M dot. We need M dot. When we consider the PM, F equals F of t equals Fc plus Kp over 2 pi M dot of t. And Kp over 2 pi is pi over 2 over 2 pi, no problem with this. The problem is with M dot of t. M dot of t here, the differentiation of M of t will be delta function. So because there are sudden changes in M of t here goes high suddenly, so the differentiation of this will give you delta up. It goes down suddenly here, the differentiation of this is going to give you delta going down, delta up, delta down, so it will be deltas. So the differentiation of M will be delta up, delta down, delta up, delta down, and in between, what's the differentiation of a constant? It's 0. So M dot of t is a series of deltas. But what does it mean when you have here in the expression of the frequency a delta? Does it mean that you are going to get an infinite frequency? So if you substitute delta here, how can you sketch this? This is confusing a little bit. This is a little bit confusing because if you get a delta in the expression of frequency, we don't understand the meaning of this. The meaning of this does it mean that the frequency is going to go to infinity? And if it is going to go to infinity, how are we going to sketch it? So this is a little bit confusing. And as I said before, whenever you are confused, go back to the basic rules, to the basic equations. So let's go back to the basic equation of the PM. Now we are discussing the PM, right? The basic equation of PM says that phi PM equals A cosine omega c t plus Kp M of t. So it will be A cosine omega ct plus Kp is pi over 2. And M of t can be either 1 or -1, right? 1 or -1. So this will give you two cases. When M of t is 1, this will be A cosine omega ct plus pi over 2, which is negative sign. Negative A sine omega ct. When m of t is -1, this will give you a cosine omega ct minus pi over 2, which is sine, a sine omega ct, right? So now our PM signal will be either sine or minus sine, sine or negative sine. Both of them with the same frequency. So the frequency is not going to change. The frequency is always omega c, it's fixed. And this is different from our understanding here where we got frequency equals delta and we thought that the frequency is going to go to infinity. No, when we went back to the basic rules, we found that the frequency will be always fixed. But when m of t changes from being 1 to -1, the modulated signal will be, the PM signal will be, instead of negative sign, it will be sine. So when m of t is 1, here in this region, you are going to get negative sign. And as you see here, if we focus a little bit on this, you will find that we are plotting a negative sign here. And then when m of t is negative, you are going to get a sign. And then again positive, you are going to get negative sign. So now if we focus a little bit on this, let's zoom a little bit. Let's zoom a little bit here. And let's get the pen. Okay? You will find that here we had a negative sign, so we started from plotting negative sign. Starting from this point here, negative sign will be sine. So you will notice that we have a sudden change of the phase here. From being negative sign, it was supposed to go down, now it will go up. We have a sudden change in the phase, okay? I'm not sure, I'm not going to zoom again. But again, starting from this point, we'll have negative sign again, and again we are going to get a sudden change of the phase at this point. So now we sketch the signal, but let's go back again and try to understand why we got a delta in the frequency here. What's the meaning of delta that appeared in that frequency expression here? This sudden change in the phase, appears mathematically as if you had a frequency infinity. When the phase changed suddenly, from one phase to another phase suddenly, this mathematically, it can be expressed as an infinite frequency. It's as if the frequency went to infinity. If the phase changed in no time, if the phase changed by pi over 2, for example, in 0 time, we know that the frequency is the differentiation of the phase. If the phase changed suddenly at no time, this means that the frequency goes to infinity mathematically. That's why in the expression of the frequency here, you found that we got some delta functions. These delta functions actually didn't mean that the frequency will actually go to infinity. No, these delta functions were meant to say that there will be a sudden change in the phase. And this sudden change in the phase mathematically appear as if the frequency goes to infinity. So when you change the phase suddenly, it appears mathematically as if the frequency goes to infinity, because the frequency is the differentiation of the phase, right? Omega or f. So we can say that f is 1 over 2 pi, the differentiation of the phase. If the phase changes suddenly, with time this will give you, mathematically it's like the frequency goes to infinity. But in reality, the frequency doesn't go to infinity or anything. The frequency is fixed, but the phase changes suddenly. So this is the explanation of this example and the explanation of why you got delta functions in the expression of the frequency. And as I say, always, if you are confused about anything, go back to the basic equations and you will find that everything is clear. See you in the next video.